All right, so I have my microphone here. It's connected up to Logger Pro, and I have a Fourier transform, an FFT. So this is a special kind of graph that is designed to show frequencies that are being excited, and you can see what's going on here. Is on the x-axis is plotted the frequency that this microphone is recording, and on the y-axis is the amplitude of that frequency. So a taller bar means that frequency is a larger portion of the energy coming out of me. And sound, we tend to think of as, well, let me just play you a note, okay? So I want to play a single note. Let's do that. Play an A. All right, so that note that I played was an A, and I hope that you noticed that there was really more, like there's a lot of kind of noise in the room. And actually, if we're very quiet, we'll see some noise in the room. Is all the way down near 0. But if I zoom in on it, it's not actually down near 0. It's oscillating near 60 hertz. And it looks like the resolution of this isn't ideal. But 60 hertz is the sound that our devices operate on. So just like that tuning fork was able to make a noise when I vibrated it against the table, the 60 hertz hum can happen there. So if I'm going to play a 440 hertz A. So let's change this to 500. And now when I play this note, look for the spike around 440 hertz. Okay. And if I extend this out, now I'm going to take this all the way out to 5,000 hertz, which is a very high note that I'm probably not capable of even singing if I tried. And I play this note, and that 440 hertz peak is really the dominant peak that's there. So there's another peak that was, I don't know, a couple other peaks. This was not actually up. I downloaded this 440 hertz from the internet. So it's apparently not a pure note that is only 440 hertz. But what you're probably noticing as you look at this is that my voice is not just exciting one frequency. So my voice is operating way less than 440 hertz, right? 440 hertz is all the way up here. La, and I talk all the way down here. So, but there's, right, my windpipe is a cavity that can have many different resonant frequencies. So I don't just excite one resonant frequency. And actually, when I sing 440 hertz, la, you can see that there is a peak around 440 hertz. But then there's all these other peaks. And actually, all of the peaks are equally distanced between each other. So look for that when I sing my note next time. La. So there's something at 440 hertz. There's something at 880 hertz. There's something 440 hertz above that and 440 hertz above that. And that hopefully makes sense from these formulas that we were using last time for how resonance sets up in a column like this. So if I show you this this thing from before, right? This lowest frequency, the fundamental frequency, the first harmonic, that's 440 hertz. But the second harmonic is 440 plus 440. The third harmonic is 440 plus 440 plus 440. And so we keep seeing these kind of additions of all of the resonant frequencies. And actually, we don't stop at 3. We go 4, 5, 6, 7, 8. This actually goes out as far as the human ear can detect. So I want to play a few different instruments, and I want to play them all at this 440 hertz A, so that you can see what the difference is in how they register. And like, this is how we perceive sound quality, which is why I wanted to talk about this, right? Why does a recorder sound different than a violin? It's not because the fundamental frequency is different. It's because we can hear all of the different harmonics and how all of that sound quality merges in our head makes sound different. So I don't know how to play an A in a recorder, but I do know how to play an A in a violin. So we'll play an A in a violin and watch what the frequencies are that are excited. So in a stringed instrument, and I will play it again so that you can notice, right, all of these frequencies are more or less equally stimulated or excited. So the fundamental, the first harmonic, second harmonic, third harmonic, fourth harmonic, etc. They all have peaks that are about the same height. I can make the same note if I pluck the string. So I'll do that. And that sounded very different to our ears, and it also had a really different combination of things that were excited, frequencies that were excited when I plucked the note. Okay, and if you've ever listened to a violin, there is a difference in sound quality that violinists can make by doing what's called vibrato. So we do vibrato by shaking your hand like this. And what I do when I shake my hand is I move it back and forth really quickly. This very subtly changes the length of the string. And that change in the length of the string is what makes it sound nice. So I'll try to do that. So this isn't going to be something that would be something we pick up on this FFT since it's broadcasting all of these things. But that's how the different things work here. And while I have this thing up here, I'll also point out some things about the violin that make the strings work differently. So last time we talked about how the speed of a wave on a violin depends on the square root of the tension force divided by the linear mass density, if you remember that equation. And so linear mass density is this thing about the tension, or the thickness of the string. And if you look at this violin, you see that actually there's a string here. You can see it down here. You can't even see it up here. This is an E string. It plays a very high note, and it's very narrow, right? It has a very small mu, a very small linear mass density. Whereas down here, this is the thickest string, and it plays the lowest note. So the different strings have different thicknesses, and those different thicknesses means that a wave travels back and forth at a different speed, which means that the fundamental frequency of these different notes will be different. The other thing that influences the note that is played was the tension in the string. And so that is what we do here with these little knobs. So if I change the tension in the knob, so I'm going to loosen the tension in the knob, and you can see it really changed the note that was being played. If I increase the tension in the knob, go back up. Okay. Let's see what else I wanted to do. Evolutionarily speaking, people have wondered, why is it that we can hear, the limit of human hearing doesn't just go up to 5,000 hertz. That's what I have plotted here. The limit of human hearing actually goes up as high as 20,000 hertz, which is amazing, right? Voice is a few hundred hertz at best, right? So why do we need to hear all the way up to 5,000 hertz? And the answer lies in the development of the ability of us to develop our language, okay? So I'm going to sing the same note, but I'm going to make different vowel sounds as I sing that note. And I want you to watch how the FFT, the distribution of the different frequencies that are excited by the shape that I make with my mouth, right? This is the open end of my tube, and if I have a shape that looks like this, or a shape that looks like this, that has makes a very different sound quality. And let's watch what happens. So we'll go E, oo, la, o, e, ah. So hopefully you're seeing what's going on is like the fundamental, that note down there near 400 hertz isn't changing, but the way that we can interpret And the way that we hear and understand what people are saying is we need all of those resonant frequencies up there to add them together. A couple of years ago, there was a video that made the rounds about Laurel versus Yanni. I don't even know if you remember it anymore, but I'm going to play it for you. It turned out that different people heard this recording as different things. So I want you to listen to this and decide if you hear someone saying Yanni or Laurel.
Laurel. Laurel. Laurel. Laurel.
So I very clearly hear Laurel. I have no idea how anyone could ever hear Yanni and that. But a non-trivial percent of the population actually does hear Yanni. And they actually tend to be the younger among us and those who have not been to as many rock concerts or listened to loud music. To explain why this is a clip of what the sound looks like. So you can almost think of this as an FFT, where up here on the top, these are the low frequency sounds that are being excited by that sound clip, and these are the high frequency sounds that are being excited by that sound clip. So I'm going to play it for you.
Laurel. Laurel.
Okay, so now,
Laurel. Laurel.
So what he did there is he excited only this sort of the low frequency, the low notes portion of the clip. And the next thing he's going to do is isolate this high frequency portion of the clip down here so we can hear what the high frequency sounds sound like. And if I listen to that, I can start to hear Yanni just from these high frequency notes. Okay, I'm going to play the Yanni one more time because that's pretty hard for me to hear. All right. So that's the answer to the Laurel versus Yanni debate from a couple of years ago, is that the notes that you are most sensitive to, so if you can hear high notes better than the average person in the population, then you'll actually hear a totally different word. So this is how language works in our world. Okay, that's probably enough playing around with FFTs. Let's do a couple quick checks. So pause it, get your answer, and we'll go over the correct answers once we're done. So which tube has the lowest fundamental frequency? And that is the tube that is closed on one end. Okay, so I have misplaced my equation sheet, but you should probably get out your equation sheet. Right, so the fundamental frequency here has to have pressure nodes at the ends. So this is where atmospheric pressure is. So it looks like that. Okay. So we'll say that, and we know that lambda 1 is 2L. And that actually doesn't tell me about frequency. Okay, so in order to think about frequency, let's think about the formula for frequency. Remember, there's this formula for the velocity, which is distance over time. And when we plug in distance, which is wavelength, and time, which is frequency, we end up with a formula that looks like that. Okay, so the speed of sound, this is constant. Right, this does not vary from one tube to the other. It's about 330 meters per second, which is pretty far. You can think of, and this is we're comfortable with this idea that sound travels at a certain speed, because we know that when I yell, it can sometimes, there's echoes that can bounce off of walls, so sound kind of travels at a certain speed, but it travels the same for all of the different wavelengths. Okay, so it has this relationship here, which means that we can infer, right, if this is the same, if the frequency goes up, then the wavelength must go down, and vice versa. Okay, We didn't talk about a closed tube, but here's what a closed tube looks like. Well, actually, let's do this one at the end because we did talk about this one. So we know that there has to be a pressure node at the open end, and there's a pressure antinode at the closed end. So this one looks like this. Okay, and here we said that lambda, the fundamental frequency, the fundamental wavelength, is 4 times the length of the tube. So if the tube is closed, we must have 2 pressure antinodes right here. So our lowest frequency, lowest wavelength will look like that. But this still is just a half a wavelength. It looks a little bit different than that, but if this is what my wave is looking like, so there's sort of the part, I'll isolate that part, that's half a wavelength. This too is also half a wavelength. If I draw a full sine wave, right, in part A, I've just isolated this portion, which is half of the wavelength. In part B, I've been isolating this part of the wave, which is still half of the wavelength, okay? So the closed tube has the same equations. It's just that there's a pressure antinode here instead of a pressure node here. Okay, so if we want to figure out which has the lowest frequency, I guess we've already shown you the answer, but they both have the same length. So let's just figure out, so V is lambda F, and if I know that this wavelength here is bigger for this tube, then that must mean that this frequency is smallest for that tube. So this will be a smaller frequency, and we perceive small frequencies as low notes. Have you ever been to a church where there's like an organ, and there's those pipes on the wall for the organ? They're very long and they're very fat. The longest, fattest pipes will be closed on one end, and those are the ones that are making the lowest notes that the organ can play. Okay, the next one is which of the following changes will increase the frequency of the lowest frequency standing wave in an open O tube? So you are going to need to find a table here, which is this one, to be able to answer all of these things. Okay, so which will increase the frequency? If we close one end of the tube, we just discussed that that does not increase the frequency, right? It decreases the frequency. So let's get rid of that one. Replacing the air in the tube with helium. Okay. So let's use your intuition about this. If somebody inhales helium gas from a balloon, what happens to their voice? It gets higher? I'm not going to demo that one for you. You just have to believe me. You can go look up all sorts of YouTube videos if you want. Right, so I know that this has to be true. Replacing the air makes my voice get higher. So let's figure out why. We're going to figure out why from this table of the speed of sounds in various materials. So we have that V is lambda F. So the wavelength that is resonant for my windpipe does that change? Windpipe doesn't change in length, so no, this stays the same. Okay, so this stays the same. So if V goes up, then F goes up. If V goes down, then F goes down. Okay, so V has most certainly gone up, which means that F must go up to match. So the frequency has gone higher, and we perceive that as a higher sounding note. And what if you reduce the length of the tube? So we have, pull up these equations from the last time here. If I reduce the length of the tube, so I have that lambda 1 is 2L and V is lambda 1 F1, and I'll plug in my 2L for here. You have your equation sheet for this, but I can't find mine, so I'm going to have to derive my own relationship, but that is there. Okay, so I'm going to solve this for f, and I'll get that f1 is v over 2L. Okay. So if I reduce the length of the tube, if that goes down, the number in the new denominator goes down, which must mean that this whole value here gets bigger. That gives us a higher pitch too. That will increase the frequency. So C works. Increase the temperature of the air in the tube. We don't have much in the way of this. Oh, there we go. So air at room temperature and air at 20 degrees Celsius. If you look here, we'll see that the speed of sound is actually getting slower the colder the air gets. Okay, so if we make it hotter, that's like going from a low one to a high one. Okay, so a hotter temperature is faster v. So we are coming back to this equation again, right? So we have a faster v, which must mean that the f has gone up, and that's a higher pitch as well. So all three of those will work. What has a longer wavelength? 400 hertz sound wave in air or water? So pause it and figure out what you think the answer is. And here we go. So we'll use this same equation, which is V is lambda F. Okay, and we'll come back to say the lambda 1 is 2L. So we can enter kind of, those are the two equations that might matter here. We have 400 hertz, so the frequency stays the same. So that must mean that the bigger V is the bigger wavelength, is the longer wavelength. So we need to figure out where the bigger V is. Air is 330, 340. Water is much bigger. So the sound wave in water actually is much bigger than the sound wave in air, much faster than the sound wave in air. Back in the day when we used to, leave our houses and go on public transit and stuff like that, I took a trip to New York City. So for every medium, right, air is kind of the slowest here. And as we get to denser and denser media, the speed of sound gets faster and faster and faster. So you can actually hear that the speed of sound gets faster. I've been, like, if you go down to the subway tunnel, you sit there and on a hot summer day when it's miserable, maybe this is something you can pay attention to, right? When the subway is, when the car is approaching, you'll hear the sound wave of the car propagating along the rails before you hear the sound wave from the car. So just, I don't know, 3 or 4 seconds before I hear the sound of a subway car coming, but it's not quite right. It sounds a little different. And that's because it has been sort of resonating against the sound wave that's propagating on the rail rather than the sound wave that's propagating in the air. Okay. So how do ultrasounds work? This is how ultrasounds work. Ultrasonic, right? That is just a sound wave that has a frequency above the limit of human hearing. So when we do ultrasounds, we send waves into sound waves. And this is a picture of obviously a uterus, but we use ultrasound for all sorts of things when we want to have a non-invasive way to image something. We use different wavelengths of waves, and knowing how fast the wave can come back can tell us where there's an object. And if knowing that the wavelength never did come back, that's where we know that's where it colors black. So we can get sort of a distance map for how far away objects are, judging by how we use our wavelengths. Okay, so I have what frequency is required, and to get this 50 millimeters here. So let's go ahead and go through this. So we'll use the relationship that is V is lambda F and solve that for F to get here. And we do the speed of sound divided by the wavelength, and we get that equals 3.1 megahertz. So ultrasounds use frequencies in the range of 1 to 200 megahertz. And so here, for this problem, we were looking for, we wanted to be able to see detail that was on the order of 0.5 millimeter. And that is what the wavelength here is useful for. So detail that is, if we use different wavelengths, then we'll see detail on different space scales. Okay, so higher frequencies here, and thus shorter wavelengths, they can show finer detail. Lower frequencies show lower details. And megahertz, right, that's 10 to the 6th hertz. The limit of human hearing is 20 kilohertz, so 20,000 hertz. So 3 million hertz is something that is so far above the limit of human hearing that we don't worry about things like babies being able to hear it or something like that. The last topic we are going to cover in waves and sound is interference of sound waves and beats. And so we've already introduced everything that we need to know to be able to do this. If you remember that demo that I showed in the last, that I've showed previously, where I moved the two speakers in and out from each other, and you heard those loud, soft, loud undulations. So there's these regions where there's constructive interference, where peak and peak meet each other. But then there's also regions of destructive interference, where a peak and trough meet each other, and you hear something, something quiet. But when you have two frequencies that are almost exactly the same note, but not quite the same note, you can hear something called a beat. So what I mean by that is, let me play you a beat. We'll go, let's see if that decides to make it. So there's my good old 440 hertz sound wave again. And let's play almost the same note, but not quite the same note. And what I want you to listen for is hearing it get loud and soft and loud and soft and loud and soft. Do you hear that? So that is that these two notes are very close to each other, but they're not exactly the right note. And I think guitar players use this to help them tune their instrument. They know when their note is almost in tune because they'll start to hear these beats. And we can actually tell how far apart these are by counting how many beats, how many cycles per second we hear that undulation. So let's play it again, and I want you to figure out about how many times this is oscillating per second. So I hear about 4 beats, right? So it's going. So I'm going up and down with my hand about 4 times every second. So I can actually use this. Now I'm going to move one of these notes and try to make the number of beats change. Now there's more beats. Do you hear it? So I went the wrong way. So let's try and make there be fewer beats. Oh, now there's way too many. Now it's undulating really quickly. And now that the two notes are very clearly very different from each other, I no longer hear beats because they're too far apart. So let's move back up. And now they're the exact same note. And the way that I know that they're exact same note is because if I listen, I don't hear a beat. But even if it's just off a tiny little bit, I hear that beat. All right, so that's what beats are. And the way that beats work is by patterns of constructive and destructive interference, just like the patterns of constructive and destructive interference work here for when I move the speakers around the room. Okay, so we have some regions where we have two waves that are almost the same frequency, right? So they have almost the same wavelength. It looks like the darker colored one is a little bit longer wavelength than the lighter colored one. So there's these regions where, and they're both traveling waves, so they're traveling to the right, and there's these regions where they overlap and they almost completely cancel each other out. Okay, so this is a region, the time when they destructively interfere. So that's when we hear quiet. Whereas over here, that's a region, a time when they are constructively interfere, so that's when we hear it loud. And so if you look at sort of the sum, and this is what we hear, of the two waves, there's this pattern of quiet and loud and quiet and loud that's like a whole nother wave that's superimposed on the top of this wave, which is pretty cool. So it sounds really complicated, but actually the problems with these are super easy. The beat frequency is the absolute value of the difference between the two frequencies. You cannot tell from this formula if the frequency is larger, which one is larger, right? There's an absolute value here. You can't tell if F1 is bigger than F2 or F2 is bigger than F1, but you can tell what the difference is between the two frequencies. All right. So pause it, and when you're ready, open it up and come back. So we'll just straight up use the equation I just put on the previous page, which is F beat is F1 minus F2, which is, I don't know, which one do you want to call F1? It doesn't matter. So 340 minus 341, which is -1, but we'll take the absolute value. And that beat frequency will be 1 second. All right, and that is the end of everything that we're going to talk about this semester for sound and waves.